Okay, now having just spent several minutes talking to you about how this op amp has so much gain, 200,000 or more, a million sometimes, I'm not going to tell you that we almost never use that full gain. I refer to it here as the raw gain, or sort of the total gain of the op amp. Is honestly, it's so much that we can't use it. You know, it really is too much for us to make practical use of. Plus, and here's another problem, it's pretty variable. The gain could be 200,000 on one chip, it could be 205,000, 210,000, 215,000. We need a reliable and precise way of controlling the gain of the circuit, even if the amplifier gain itself, A, changes. Now, if anybody ever says to you, hey, you're an electrical and computer engineer, how do I make sure that my system is very precisely controlled and very repeatable? The answer is negative feedback. Negative feedback is one of the miracles of electrical and computer engineering because it causes the system to be very stable and very reliable. You simply take a little bit of the output and you add it back in to the input with a negative sign. A good example of this is a thermostat. You know, as the furnace or the heater is running, it causes the temperature in the room to increase, but then that causes the heat to be decreased. So as the temperature in the room is increased, the thermostat is a sensor that causes the heat itself to decrease. So that's negative feedback. The heat in the room is the output of the furnace, but it's also the input to the thermostat. So we have a feedback loop. And in fact, negative feedback is almost always what we're going to use. So we often just refer to it as feedback. But if you ever hear feedback, you can assume that it's negative feedback. You know, if you're talking to your boss, you want positive feedback. If you're training a pet, you want to use positive feedback. In electrical engineering or like computer engineering, you always want to use negative feedback. In fact, positive feedback is almost never a good idea because that would be like as the temperature in the room increases, I'm going to increase the rate at which I use the furnace. And that leads to very high instability. And that's like if you get the microphone close to the speaker, that's known as feedback. That's actually positive feedback because it's actually amplifying the speaker through the microphone back to the speaker again. And you know that's very unpleasant when that happens. So what we're going to find then is that the practical op amp circuit, and I'm going to go ahead and skip ahead to figure 4 because this is really important. The practical op amp circuit is always going to have a feedback path between the output, which is over here, back to the input. And not just any input, but always the inverting input, always the negative input. So that's very important. If you ever see a circuit where the feedback path is going into the positive input, you know that circuit is probably poorly designed. So feedback path from the output to the negative input will almost always be the case when you're talking about an op amp circuit. So if this were the case, one extra thing that I want to consider here. Let's imagine if I go back up to equations 2 and 3. So there's one more thing. Oh, sorry. Where is equations 2 and 3? Oh, they're right here. So I know that if the output needs to be, you know, a reasonable number, like say about 5 volts, and if the gain, the raw gain is like 200,000, then that means that the voltage difference between V plus and V minus needs to be a very, very small number, something like 25 microvolts. Well, with the feedback path in place, we know that the output is going to be a reasonable number, and therefore that means that the inputs are going to be approximately equal to each other. And that's a really important assumption because it's one of the 2 cardinal rules. And I don't have very many cardinal rules, but I do have 2 cardinal rules for analyzing op amp circuits. The first one, we know that the input impedance is very high, and therefore the current flowing into both input terminals is approximately equal to 0. And the second one was just derived from equations 2 and 3. The voltages on the 2 inputs are approximately equal to each other. That second one is really only true if you have an appropriately connected feedback path, but for all of our circuits we always will. So that second cardinal rule will always be valid. So it turns out that those don't seem like they're very profound cardinal rules, but let's look at an example of how they are. What I've done here in figure 5 is I've simply replicated figure 4, but I've added a few annotations. So I know, for example, that I have this, I'm going to label this as I sub n, I'm going to label this as I sub f. I know that this positive terminal, the non-inverting input, is tied directly to ground or tied directly to the reference voltage. So therefore, that's equal to 0 volts. And according to the second cardinal rule, the voltages on the 2 inputs are approximately equal. Well, that means that this voltage is also equal to 0 volts. Let me zoom in on that circuit so we can see it a little bit better. Maybe I can't zoom in very much, but we get 0 volts right here. So that's very important. I also know that there's no current flowing into this terminal. That's the first cardinal rule. The current flowing into both input terminals is approximately 0. So we have 0 amps flowing in here. We have 0 volts at this terminal. Well, I can do Kirchhoff's current law at that node. I'm going to have current IN plus current IF, and then I have no amps here. So that just means that IN plus IF has to be equal to 0. So I know that IN plus IF plus 0 is equal to 0. And therefore, IN is equal to negative IF, just a little bit of algebra from equation 4. Well, can I rewrite IN? Well, IN is simply the voltage difference across this resistor divided by that resistance. So that's VN minus 0 divided by RN. So we have VN minus 0 divided by RN. And then how about IF? IF is this voltage, but that voltage is just V out. So it's V out minus 0 divided by RF. So V out minus 0 divided by RF. Don't forget the minus sign carries down. And then I'll do a little bit of simplification, just a little bit of algebra, and I find that V out equals minus RF over RN times VN. Equation number 7 is super important. In fact, if I were you, in your notes, go back up to the top of the previous page, back up to the top of page 4, and write that equation right here next to this inverting amplifier. I didn't really know how to put that equation there without having spoilers, but now that you've seen it, right here, put V out equals minus RF over RN times VN. That way, when you see the inverting amplifier, you'll always know what the equation is. And you might say to yourself, oh man, I can't remember, is it RF over RN or is it RN over RF? And that's something that there's a trick for. So it's RF over RN. So if you go back up here, you can see that RF is physically higher in the circuit than RN. And it turns out that in the equation, RF is physically higher than RN as well. And so that'll help you to remember that RF is higher, RN is lower. And so therefore down here, you see that RF is higher and R1 is lower. I'm sorry, that's the wrong circuit. RF is higher, RN is lower. So that's one of our 4 building block circuits, one of our 4 most important circuits. We can consider 3 others as well. We have the non-inverting amplifier, which is this configuration right here, and that has a gain that looks like this. Now you might say, why is one of them called inverting and the other one's called non-inverting? Well, the inverting amplifier has a negative sign in front of it, and so therefore if Vn is positive, then Vout will be negative. Well, that can be troublesome if it's DC circuits, but sometimes that's what you want. But the other thing to know is that if this is sinusoidal circuits, a negative sign doesn't really do very much. It just shifts the phase. It doesn't really change the amplification at all. And down here, we don't have a negative sign, so this is a non-inverting amplifier. And then we can have also what's called the voltage follower. The voltage follower just simply says Vout equals Vn. And I know that when I was sitting in your seats, I said, well, why in the world would I want a circuit where Vout equals Vn? That's just called a wire, right? I could just connect a wire from Vn to Vout, and that would say Vout equals Vn. But notice that there's one other thing that the voltage follower does, and that says, I'm not going to take any current from Vn. So I can sense what's going on with Vn, and I'm not going to disturb it at all. If I just had a wire, I have no idea what's going to happen with the current that's going to be drawn from Vn, and that could change the behavior of the circuit. But because I'm taking this directly into an input of the op amp, this current is 0, and therefore I'm sensing the voltage, but I'm not affecting the voltage. And the Vout then will just simply follow Vn, and I can do whatever I want to over here because the op amp can deliver enough current to deliver, to be able to power an awful lot of different things. And then finally I have the summing amplifier. And the summing amplifier has more than one input. It can have 2 or 3 or 10 inputs. And the function is just going to be RF over R1 times V1, RF over R2 times V2, RF over R3 times V3, RF over R4 times V4. And then there's a minus sign in front of the whole thing. So it should actually be called the inverting summing amplifier, but people just call it the summing amplifier. So this is the 4th of our building block circuits. We've derived the relationship for the inverting amplifier, and in the example problem you're about to do, you'll derive the other 3 as well. So both the non-inverting amplifier and the voltage follower send the voltage directly into the non-inverting input. Let's go back up and see that again. We're sending this directly into the non-inverting input, and here we're sending this directly into the non-inverting input. So both of those will draw no current from whatever it is that they're sensing, whereas if I go back up here to the inverting amplifier, it can be drawing current. There can be current coming through here, and I don't really know whether or not that's going to be changing what's going on in the original circuit that I'm sensing. So I think that you're ready now to do a couple of examples. This first one is going to ask you to derive, or we're going to derive together, the relationships for the other three building blocks, and then it's time to apply them to be able to design an actual op-amp circuit.